Thank you guys all for being here. I'm going to talk to you about this really big idea of basically how do you put your data into a large language model. We titled it the unsung hero of AI, but really what this is about is how do you work with your data and how do you work with large language models. I don't have a demo, so everybody put your thinking caps on. I'm going to walk you through some conceptual things. A little bit of background about me. That's my LinkedIn QR code if you want to go find me. I'm the developer advocate at Zilliz. My background is mostly machine learning, specifically natural language processing, which is kind of why I'm working on large language models now. A little bit about Zilliz. We are based in Redwood Shores, about 20 minutes south of here, 30 minutes south of here, maybe an hour depending on traffic. We were founded in 2017, and we are the key maintainers of many projects, but the ones you want to pay the most attention to will be Milvus, the open source vector database, GPT Cache, this is a semantic cache that helps you save a lot of money in production, and VDB Bench, which is vector database benchmarking. I'm going to give you a QR code to that at the end so you can do your own benchmarking. So today we're going to cover 4 topics. Why do you need a vector database? How do they work? And how do you evaluate a vector database solution? And then at the end, I'll give you some tips for getting started, and I'll give you my own opinion on where the market is going. Okay, so why do you need a vector database? Let's look at these sentences. How does your company increase its bottom line? How does your company make more profit? How does your company increase profitability? These 3 sentences are actually all the same question, semantically, right? If I asked you any of these 3 sentences, you would know that these are all the same question. But if you were to use keyword search and you were to search for the word profitability, you would lose the first 2 sentences. Whereas with a vector database, with semantic search, with vectors, you will be able to find all of these sentences. And it's not just text. You can also do this with images. For example, this is my favorite artist, Taylor Swift. If you were to go and look for this image of Taylor Swift in this database, you could get back these most similar images of this celebrity, of Taylor Swift, if you had a database of celebrities. So it's not just text, it's not just images, it also works on audio data, it works on video data, and it works on typically any type of unstructured data you can think of, as long as you have the embeddings model that can handle that kind of data. And unstructured data is pretty much everywhere. I'm sure that you guys have been at this conference. You've heard many spiels about this now. This is going to be the most important type of data to take advantage of in the next 10 to 15 years. An example of how you can kind of take advantage of a vector database, take advantage of unstructured data. In this case, we use markdown documents. We built an open source chatbot that allows you to chat with any open source repo that we have on there. If you maintain an open source repo and you do not see it on OSS Chat, the link is osschat.io. If you do not see it on OSS Chat, simply submit something and we can put it in there for you. But the example application that I really want to that I want you to think about conceptually here is, let's say you're an enterprise company and you have hundreds of thousands, millions of documents. How do you handle chatting with those documents? That's the main kind of value proposition that a vector database allows you to do, is to handle chatting with all of these documents. So how do vector databases work? Vector databases work through this thing called semantic similarity. And semantic similarity is essentially how close are 2 words in meaning. And vector search allows you to do this thing with, well, you can see on the screen I've got 4 words, queen, woman, man, and king. And I'm doing some math on them. And typically, you could probably look at this and say, queen minus woman plus man equals king. Okay, that makes sense. But how is a machine learning model going to make sense of that? It needs the numbers. And so what we're doing here, what I'm showing you here is just a very toy example. It's a 2-dimensional vector. What we're taking is the vector of queen, which is 0.3, 0.9, the vector of woman, which is 0.3, 0.4, and we're subtracting them, and then we're adding the vector man, which is 0.5, 0.2, and we get the vector king, which is 0.5, 0.7. If this is confusing, don't worry. What I want you to understand from this slide is basically vectors allow you to do math on things that are not numbers. And where do you get your vectors, right? So now that we understand what similarity search is, let's take a look at how we actually get these vectors. Typically, they come from your knowledge base, and they're fed into a deep learning model, and then the vector embedding is extracted from the second to last layer of your deep learning model. So this is why earlier I was saying you can use any type of unstructured data as long as you have the embeddings model for it. The embeddings model is very important. This is what produces your vectors, and this is probably about 90% of what accounts for your vector search. Once you have those vectors, you store it in a vector database. The examples I have here are Milvus and Zilliz, because I work at Zilliz. So how does similarity search work? So in this last slide, I talked about docs to deep learning model to vector into a vector database. So that's steps 1 and 2 in this little diagram here. Step 1, right, you transform into vectors, and then step 2, you store in a vector database. At query time, that's step 3. You do essentially the same thing as steps 1 and 2, and then you feed that vector and you query it into the vector database, and the vector database will return to you an approximate nearest neighbor search. And this means that it will give you the vectors that are, the closest in distance. Okay, so how do you evaluate a vector database? What do you care about in vector databases? Why do they matter? Why is Zilliz special? Why is Milvus special? This is my plug, right? So this is the basic functionality. This is the kind of data that you store. Everybody who's, can I see a show of hands for who's works with a NoSQL database? Okay, so pretty much everybody kind of understands what this data is like then, right? We're storing some JSON data. The main difference here is instead of querying on like a hash key and a partition key and a primary key, essentially what we're going to be doing is we're going to be querying on an embedding. And so our embedding is our main key. We are also able to retrieve through the ID, but the embedding is the main comparison tool here. It's the main thing that we're being indexed on. So why would you not use a SQL database or a NoSQL database with a vector search library? I would suggest you take a picture of this slide because I'm actually not going to say any of those sentences. What I'm basically going to tell you here is let's just take a moment to understand how SQL databases and NoSQL databases work. What essentially happens is you give it a key, and it goes in and says, do I have an exact match to this key? And if it does, it will return to you that exact match. However, if it doesn't, then it won't. So in a vector database, you almost never expect an exact match. And also, when you query, you are expecting to do thousands or hundreds of thousands of calculations, of computation. And SQL databases and NoSQL databases have no computational backend. So you need a specialized infrastructure in order to effectively query vectors, especially at scale. Why not use a vector search library? Does anybody here know what a vector search library is? Of course, Otten, you know. So vector search libraries are essentially a part of a vector database. This is one of the ways that you can search your vectors. It provides a way to index and to query your vectors. And Milvus offers, I believe, 9 ways to do this, 9 ways to do vector search. But the reason why you would use a vector database and not just a vector search library is that vector search libraries have no infrastructure on the back end. They have nothing to support large-scale querying. Why do I keep talking about scale? Because that is exactly what Milvus and Zilliz is built for. Milvus/Zilliz is built to be the vector database at enterprise scale. You really start to see performance differences around 1 million vectors, and you start to see real performance differences once you get into the billion scale. There's only a couple companies that can say they even have billion scale, and you'll see some stats in a second. So what makes Milvus scalable? What makes Milvus different? Essentially, we have a cloud-native distributed system architecture. I know there's a lot of jargon, but what that really means is we had a V1, and we saw that scaling was difficult with that. And the reason why it was difficult was because we didn't initially think to put it onto the cloud-native structure where you're spinning up a bunch of Kubernetes pods. And so now what we've done is we've done that architecture change. There's also a true separation of concerns. When you're doing search, not just vector search, but any search, there are 3 concerns that you have. The 3 major concerns that you have are, how do I access my data? Or how do I create the way to access my data? This is called indexing. How do I store my data? That's storage. And how do I retrieve my data? And that's querying. And so Milvus has a separate node for each of these concerns. And this allows you to effectively scale and to effectively have, lower costs as you scale, because these things are different and you only need to do one, you only need to scale up one node to do one at a time. The last thing that's very interesting is that we have a scalable index creation. So Milvus uses a very interesting index strategy where we index only 512 megabytes at a time. And so in this case, what happens at query time is, so we're constantly building indexes as we ingest data. And at query time, we will parallel search all of this. So I want you to put your thinking caps on and just imagine that you have 100 gigabytes of data. Would you rather search 100 gigabytes of data all the way through linearly, or would you rather do 200 parallel searches that coalesce at the end over 512 megabytes? I think it's pretty clear that you would rather do the latter option. That's a near constant search time. Just some stats, and then I'm about to wrap up. So we are the most popular vector database in the world. We have 23K stars, over 23K stars on GitHub, over 5.6 million Docker pulls, and over 50 projects with more than 1 billion vectors in production. Tips for getting started, pull out your phones. These are some QR codes here. So if you want to get started benchmarking, we have an open source benchmarking tool. I always tell people, don't take my word for it. Pull the repo. Do your own benchmarking. Bring your own data. You don't need to believe everything I say. You can find out for yourself, right? Seeing is believing. And then on the right over there is a code demo that I made. And this is an advanced demo. So I'm sure you've seen many introductory demos. I wanted to give you something that is more enterprise scale. This is multi-document querying. This allows you to query on multiple documents as if you were an enterprise who had hundreds of thousands of documents. And that's pretty much it, I think. Yep, that's pretty much it. So thank you very much. Oh, questions?
I was curious to know, so vector databases have existed for a while, even before the whole LLM revolution. And they've been known to do like nearest neighbor searches and getting like similar embeddings. I'm curious to know, in the new world of LLMs, is there anything beyond like nearest neighbor searches that have emerged from an API standpoint that vector databases should natively support?
Oh, that is a great question. Are there any new ways? I don't know if there's any ways that vector database should natively support. I think that the role of the vector database should be to support your semantic similarity search. However, we have seen that a lot of people add re-ranking, right? So Haystack had their talk yesterday where they were talking about like adding like a re-ranking engine that does diversity ranking afterwards. And that's a typical post-processing step that we see. Cool. Any other questions? Thank you.